Not so long back I made a video about building a basic storage oscilloscope add-on using a 6502 microprocessor. This was not a completed project but a concept, concluded by demonstrating a working example showing just how well a simple add-on can actually work in practice. Plus, for anybody wishing to move this idea forward for their own usage, it could be quite straightforward to produce a usable device with very few changes needed. For this video we're visiting a similar add-on idea for a simple oscilloscope in the form of a trace doubler, essentially giving a basic single beam oscilloscope the similar facilities to those on a more advanced variant, thereby having two separate traces displayed simultaneously on the tube face. For some time I mulled over the idea of doing one of these, in essence to see just how well it would actually work, and don't do anything particularly complicated, and produce a usable example, bearing in mind that at the radar room a couple of our demonstrating workable exhibits already have multiple line displays on cathode ray tubes. However, in this example I'm going to show here, it's not dedicated to a particular unit and theoretically could work with almost any standard single beam oscilloscope with basic facilities. As with the storage scope video circuit, this is not a complete project but a working demonstration unit that will hopefully give any prospective builder a good idea of the sort of performance one can expect from a simple circuit, and equally importantly, what additional pieces of circuitry might be needed to make the thing into a usable and useful add-on for their workbench. First and foremost, a quick history behind the basis of the project. Looking through some more practical wireless magazines, I happened upon a couple of trace doubler circuits, one from 1951, the other from 1966. The latter can be seen here as entitled An Electronic Gate. This simple little diagram at the bottom of the page shows a simple concept behind the author's circuit. There's a good circuit description here, and the schematic is revealed several pages later, and it shows a total of 4 double triode valves. Second circuit originated back in 1951. Once again, the article made an interesting read, but it's seemingly unlikely the author ever built a working example themselves due to a number of obvious omissions, including the customary parts list. There's little to choose from aside from this, aside from the fact that it uses 2 triode hexode valves, of which I happen to have several here, new and boxed examples. Plus, it also used 2 of the old EF50 pentode valves from the 1940s, and as I have a box of these things, the decision was made to commence building this particular circuit. Before taking a quick look at the schematic, please bear in mind if you're interested in making something like this, there are numerous similar circuits found on the internet using transistors. Here is the complete circuit as found in the magazine. In reality, it uses quite a simple idea, though this time an astable multivibrator sits in the middle with 2 cross-coupled triode hexodes, whilst the other sides are 2 EF50 pentodes, simply amplifying the signals going into the hexode portion of said circuit. Note that in my version of the circuit I'm using a pair of UCH42 triode hexode frequency changer valves which use a 14 volt filament, which I just happen to have here. The ECH42 variant would probably be better for anybody not wishing to provide 2 different filament voltage supplies to their valves. Talking about different voltages, aside from the HT of circa 300 volts DC and a 6.3 volt AC for the valve filaments, it also requires a negative 6 volts for the separation and control bias. Interesting. Think of the multivibrator as an electronic switch that enables and disables the hexode part of the valve which shares the envelope with each triode. There will be a burst of signal from input 1, then a burst from input 2, etc, etc. As is an internal connection between grid 3 of each hexode and the triode it shares the envelope with, the hexode will have its electron flow both enabled and disabled during each cycle of the multivibrator. One of the most important omissions from this circuit, in my opinion, is that the electronic gate portion or multivibrator only has one fixed timing setting. Obviously, for use with multiple signal frequencies and scope time-based settings, you will need more than one of these. Something would not exactly be rocket science to incorporate into a finished unit with a 2-pole rotary switch and additional capacitors. And here we go, one simple chassis with 4 valves on it, 2 EF50s at the back, 2 UCH42s at the front. It's 2 mains wires coming in the back, well not mains wires, power wires. They're going to the power supply. I didn't consider it's worthwhile building a power supply into this, so therefore it's coming from a remote supply over there. 3 knobs on the front. This one is the sensitivity from this channel, this is the sensitivity from this channel, and this one is the trace positioning. Well, it's effectively how far each one is from each other and whether they're upside down in the middle and the 2 traces join. So that's really all this is about, the separation effectively. Here we have a sync control. It's quite simple really. It simply switches the sync through to the sync output from either the left channel or the right channel. This of course is the underside of said chassis. Not a difficult circuit, but it's quite involved actually. There's quite a few bits and pieces, as you can see in there. Once again, not a lot to say. The reasoning for the tags on this side is simply so we have the output and the sync output here, the two inputs of course through these sockets here. There's the sync switch and power coming in here. That's about all we can say that there is to show about it. Here we have the thing sitting up on a pot here to keep the valves off the surface there. This is a test set 43, but it's something quite nice and old. And all we're using it for at the moment is going to be to say to check the monostable. It's a power supply over here, that's what we're driving the set with. So if we connect up the oscilloscope probe and we turn on the supply, all we have to do now is wait for the valves to warm up so that it starts working. So all we're seeing is literally it's a monostable with the two triodes in it, and this is what is going to chop between the two input signals and put them through to the oscilloscope. So at the moment it's about 50% ratio, which is what it should be. For our first experiment I thought it was a good idea to use a more modern scope, so a little bit more modern than the test set 43. So it's the best we can sort of squeeze out of the system without worrying about whether it's something that the older scope won't sort of understand from this machine. Anyway, there we go. So on our left we have an audio oscillator and a second one almost off camera on the right. The one on the right here is about 5k. We put it's sort of around about 5 kilohertz, and this one's about 70 kilohertz, just to give some idea. Now if we go considerably less than that, you start coming with all sorts of strange anomalies on the screen, and this is where we would need a different chopping frequency between the two valves here. So let's turn it on and see what happens. But first of all, the first time we're going to use it, as you can see we have no sync, no external sync plugged in. So we'll see what we can squeeze out of it just using the trigger control on the scope itself, and you'll find it somewhat limiting. Here we go. So we have two traces here. This is obviously the 5k, which is the lower one, which is this. So if we change the amplitude, yep, we can do that. And this one is the oscillator to our left, and this is about 70k. So okay, let's see what we can do with it. So first and foremost, yes, we can trigger on that, and this is coming up somehow at the top. If we drop, just out of interest, we go down low, you can actually see this is the chopping frequency of the monostable with the higher frequency and the lower. And if we use the separation control on here, you can actually see you can sort of swap the position. So now we have the high one at the bottom and the low one at the top, but unfortunately once again it's difficult to actually make it do what you want. So we use a higher frequency and hope it'll be slightly better. But once again, what I'm trying to do is show it's not really working correctly without that trigger. Whatever we do, we cannot have them both up together, and it's really difficult. I just cannot find that one. So what we'll do next is we'll plug the trigger in, and we'll switch over to the trigger coming from this unit here, and we'll see if we can achieve something a bit better. So here's the trigger lead here, stick him in there, and switch to external trigger, and well, is that any better, we ask? That's one. Let's try switching over these syncs. Oh look, we actually have something there. So now at long last we actually have a double beam scope coming through from one input. Obviously these are sensitivities, they're a little bit wishy-washy. I don't like the way they've used them as the cathode resistors to vary the gain. Yeah, okay, fine, but it's not ideal, is it? So there we go. Let's just shove those around again. If we say vary the frequency of this one here, that's just over 100 kilohertz. We go down to 10 kilohertz. But note, we're beginning to see some little sort of anomalies coming at these low frequencies. So that's the top one again. So I think that sort of says we're running out of steam here. So if we go back up to the high frequency, things are a little bit better. We can obviously extend that and we can do what we like with it. Look at the bottom, which is the oscillator on the left. And that's it there. Here we have the test set 43. And we have very much the same settings as we had. We've left it much as it is. And here we're triggering on this lower frequency here, which is once again about 5k. Switch to the other, and use a little bit of tweaking just to make it happy. And this is our upper frequency here. The HF of this isn't very good, so you can see we're obviously experiencing a few problems here trying to have a decent waveform out of it. That's why it's not a sine wave. And that's back on our lower frequency there. So basically it works, but one needs to watch out for things like the fact that you're going to have to increase the number of settings here if you want to use it seriously, and likewise watch out for the upper frequency response of an older scope like this one. As a last little experiment, what we're doing is putting two outputs from this, a square wave and a sine wave, into the two separate traces through the little box. So we can actually see what it looks like with two actually in sync with each other, so don't have to worry about the triggering at all. You can turn down the square wave, for example. There's the square wave, and then there's a sine wave. It's about 15 kilohertz. It's not that good square wave. But there we go. I think that it concludes what we've been doing with this little device. I think it's up to the experimenter whether or not they feel this would be actually good enough to warrant building it. It's not that complicated, but you've seen underneath it, you'll see the circuit, which I'll put up in a minute, if you choose to give it a go. I think it could be useful for some people for looking at certain applications. I'm not sure I can necessarily think of anything to do with this device here, but there we are. At least it's fun trying it out, and you can see how well it works, so you can ascertain whether or not something like this would be useful for your own usage. Thanks for watching.